Okay, so water flow is not only a function of hydraulic conductivity, it's also a function of pore water pressure. So what are we talking about when I say pore water pressure? Okay, so we have already talked about pore water pressure, but we've talked about it below the water table. And below the water table, pore water pressure is always positive. So this is the pressure due to overlying weight of water. So you can think about this as sort of a positive force that's pressing on soil particles and on underlying water. So we consider that to be sort of a positive force. So it forces water up, if it's in a well, for example. So this is also true for saturated soils. So in a saturated soil, pore water pressure is going to be positive, and flow is going to be due to elevation above sea level. So that, again, it's like gravity and potential energy stored in water. And then pressure head. So this is pore water pressure due to the overlying weight and pressure of water. So positive pressure. Okay, in unsaturated soils, water is retained, or it's held to grains by capillary action. So if you remember, we talked about capillary action before, so this is not only cohesion between water molecules, it's adhesion to particles. So especially in clays where you have negatively charged particles, water sticks to the sides of soil particles, and then in between those places where it's sticking, the water sticks to each other. So you've got these little water films here where you've got adhesion along the soil surface and then cohesion between the water molecules. So we think about this as, rather than exerting sort of a positive pressure or a force on the particles, it's sort of drawing these particles together. So it's sort of exerting this negative pressure on soil particles. So we consider pore water pressure in unsaturated soils to be negative, because it's no longer sort of pushing against the soil particles, it's pulling them together. So it becomes more negative the drier that soils get. So this is, again, sort of in contrast to when soils are saturated. And when soils are saturated, hydraulic conductivity and water content data are high. Pore water pressure is positive due to the weight of overlying water. And pore water pressure due to capillary action is zero, because there is no capillary action yet. It's all positive pressure due to weight of water. And in this case, water moves downward with gravity and down hydraulic gradient. Okay, so this is just sort of a different way of, or just another way of looking at this same idea. So we have an unsaturated zone up here and the water table down here, saturated zone. And down here we've got positive pore water pressure, so it's dominated by the weight and pressure of water pushing on soil particles, positive pore water pressure. And then up here in the unsaturated zone we have negative pore water pressure dominated by capillary action. So this is sticking to soils and sort of pulling the soil particles together because of that cohesion between water molecules. So these forces, these negative pore water capillary action forces, are greater, that is more negative, in fine versus coarse soils, and there are a couple reasons for that. First is because it's just stronger in small pores, so you've seen that before, water moves higher up a small straw than a large straw, or moves higher up a small straw than a large straw. So clays have smaller pores, so they tend to have more water than sandy soils, and that capillary action is greater. You've also got that negative charge on clay, so you have more capillary action going on. So not only does that mean that these forces are greater, it also means that as you move from sand to clay, you'll have more water in the soil at higher or more negative pore water pressures. So even if you're at sort of a wilting point, even below that wilting point in a clay, you're going to have more soil water, or more water still in the soil than you would in a sand, and more available water in a clay than you would in a sand between field capacity and wilting point. Okay, so drying clays even if they're dry, there's still some water in there. So drying clays still provide transport because there's more water in them for a longer period of time than drying sandy soils. So this means that at really low pore water pressures, clays will have a slightly greater hydraulic conductivity. And that's what this figure here is showing you than a sandy loam. So here is essentially negative pore water pressure, which if you have taken a soils class, this negative pore water pressure is often called matrix potential. And here's your hydraulic conductivity on the y-axis. So at not very negative pore water pressures, clay soils have less hydraulic conductivity than sandy soils. And this is because, as we talked about before, those small pore sizes making it harder for water and things to move through. But as you get down to really dry soils, the sandy loam sort of drops all of its water. The clay still holds on to it, so there is some water, whereas in the sandy soils there's no water for fluids to move through. Okay, so sort of summing up, movement in unsaturated soil, we have gas and air moving with diffusion and convection, but we're using this first order decay equation to estimate these more complicated processes, to do it a little more easily and more empirically. With water, it's a function of hydraulic conductivity and hydraulic head gradient, elevation, and pore water pressure. And the hydraulic conductivity increases with water content. So at high water content, sandy hydraulic conductivity is greater than a clayey soil's hydraulic conductivity. But at really low water contents, clayey soils have a higher hydraulic conductivity than sandy soils. And that's just because sandy soils are essentially dry, while clays still have a little bit of water in them. So with saturated flow, when the unsaturated zone is actually saturated, movement is very similar to groundwater flow. So it depends on hydraulic conductivity and gravity, so elevation above sea level, and that positive pore water pressure. Unsaturated flow then depends on hydraulic conductivity. Again, there's potential energy involved with sort of elevation above sea level or gravity, but now we've got negative pore water pressure sort of pulling water and making it stick to soil particles. Okay, and then I am going to talk really briefly about the fact that pollutants can sorb to humus or clay, organic matter or clay. We've talked about this a lot, so this is just a really brief sort of reminder that soils and sediments are sinks for hydrophobic pollutants and heavy metals, things like mercury, and these things really tend to accumulate in upper soil levels because this is where the clay is and this is where the organic matter is. So you'll end up with heavy metals like mercury, pesticides like DDT, and things with high partitioning coefficients between organic carbon and soil water, things with high KOCs. Okay, so just like in groundwater, sorption slows movement in general, but in general water moves downwards regardless, but there'll be more retention of these pollutants near the surface just because that's where the clay and the organic carbon is. Alright, so that is it for the videos for this section. So again, thanks for watching.